Hello everyone, welcome back to my channel. In these two videos, I will show you how to include spin-orbiter coupling in the band structure calculation of LED, and then I will show you what is the effect of spin-orbiter coupling on the band structure, and I will try to reproduce this plot from the literature. So in this video, I will do the band structure calculation without spin-orbiter coupling, and in the next video, I will show you how to turn on the spin-orbiter coupling. The procedure for calculating the band structure is actually the same as shown in my previous video about the calculation of silicon. You first need to relax the cell and then do a self-consistency calculation to calculate the wave function, the ground state, and then to specify some K points and calculate the bands along the K path. Then we use bands.x to do post-processing and generate the file that we can plot. To plot the band structure, I will use the Python script that I have introduced before because it has more flexibility than plotband.x. One thing that I would like to mention now is that if you want to turn on the spin-orbiter coupling, you need to use full relativistic pseudopotential, and SSSP library that we usually use does not support that. One option is to go to the PS library, which is intrinsic to Quantum Espresso, and you can just go to the pseudopotential website. This is the PS library. We need LED. So it's here. Because we want to compare the band structure with and without spin-orbiter coupling, we would like to keep the pseudopotential files similar to each other. So for the calculation without spin-orbiter coupling, we choose this one here. And then for the one with spin-orbiter coupling, we scroll down and it is here. And this is important that it is full relativistic. I have already downloaded to the folder here. You see that two pseudopotential files. So let's get started of today's video. We first do a VC relax calculation, and this is something that you may already be familiar with. And this time we choose this smearing method, and this method is very good for metal, and we know that lead is a metal, and lead is an FCC lattice, so we only have to specify one lead atom in the unit cell. Okay. So I will not run the calculation here, but it is run with this command. After we relax the structure, we can calculate the ground state. And this is the SCF calculation to calculate the ground state. We calculate the force and the stress because we will want to make sure that the atoms are in the equilibrium and the cell does not have any pressure. In principle, those are not necessary because they are ensured by the previous step of the relaxation. Everything else is quite similar except that we increase the K-point density, we lower the degauss here, and we also lower the convergence threshold here so that we get a more precise evaluation of the ground state. And here, notice that we use the normal edition of the pseudopotential file. So after you calculated the wave function, you can proceed in the band structure calculation. And actually, this is the calculation of the band. And this is a non-self-consistency calculation. You need to specify the K-point path. And we choose the K-point path because we want to compare it with the literature, so we copy the K-point path here. But of course the question would be that how to obtain the coordinate of the K-points from the name of the K-points. And for that, just as a quick note, you should first search what is the space group of the crystal. For example, in our case, it is space group 225. And then you can go to some crystallography server like this one, the Spielbaum crystallographic server, and then you input the space group, and then there will be a chart with the correspondence of the label and the primitive basis. And the primitive basis is actually what we use here, but just make sure that this is in crystal B because we express in the unit of the K-space Brillouin zone. So for example, here X is 0.5, 0, 0.5, and that is what we have here. And then L is 0.5, 0.5, 0.5, and that is what we have here. Sometimes you have something that is not written down here. You can go to some other crystallography server. Another side note is that usually due to symmetry, there will be multiple equivalent X points. So don't be surprised if you find the K points from others' file to be different. Just to think first whether this is symmetrically equivalent. Okay, this is the bands calculation. And then we go to the second step, that is to use bands.x to post-process the output that we generated. And for the input file, it looks like this. We need to specify the output directory and the prefix, and this is the file name of the output file. So after you run this command here, there will be different output files, for example this one and this one and this one. So for the Python script, we need this file as the source of data, and then this file because it contains the high symmetry points inside. Okay, so now we would like to plot the band structure. I put the script here because later we want to plot both. So let's take a look at the run.py, and the data file is in this folder, and the name is this .dat.gnu. And for the Fermi level, sorry, I forgot that you can find in the output file of the self-consistency calculation. If you scroll down to the bottom, there's this Fermi energy here. Yeah. Okay. And then the symmetry file, this is the output file for the bands.x, and we can just use the bnd plot function that is imported from bands.py, and then we also name the k points here, and let's just plot it. So this is the band structure, and then we just copy it to the Excel. And you see that it is very close to the dashed line here, and the dashed line is without spin optocoupling. Okay, so in this video I have shown you how to do the band structure calculation of LED without spin optocoupling, and in the next video I will show you how to turn on the spin optocoupling. Thank you for watching, and I hope to see you next time.